Thank you. Hi. Hi, everyone. My name's Amar. I'm an engineer at Netflix on the data platform team. And today we're going to talk about how we moved dozens of databases that were on a third-party, Postgres-compatible, distributed database to Amazon Aurora Postgres. We'll start by talking a bit about the problem, like what we actually did and why. Then we'll spend some time talking about how we did it. And I'll leave you with where we are right now and what learnings we have so far. There's a ton of content and not as much time. So I'm going to blast through a lot of this, also because I'm slightly over-caffeinated. But find me at the end if you have questions, or I can explain things a little bit more in detail. So I'm on a platform team. We work with a whole bunch of application teams, and these application teams that run the business, they work on the Stranger Things season 5, production, and a whole bunch of other things. No spoilers, please. And these a lot of these teams run, they use our databases, and particularly a lot of them ran on this third-party distributed Postgres-compatible data store. It's self-managed, which really means our team manages it or managed it, and that kind of comes with its trade-offs. It's self-managed, so we do a lot of work managing it, upgrading, and those sorts of things, and instance replacements. It's Postgres-compatible, which means it's usually Postgres, but until it's not. And so, we found that those trade-offs, plus it can get kind of pricey running such a powerful database across the entire fleet. And in most cases, you don't need it. And in the past few years, especially Aurora, Postgres has come a long way in terms of feature set, reliability, and even cost. And so we made a decision as the central platform team to move all these databases over to Aurora Postgres. And it's important to note that this is the platform team making a decision for all application teams. And so the more work we can do, the better it is, because we're asking teams to move. Additionally, it's better for the company if we take as much of the cycles and execute them ourselves and not make the app teams do it. And so we're going to go over how it works. But in general, database migrations, they're a solved problem. You copy the schema and the data, you validate it, make sure it's all there. And then all you have to do in theory is to point the application to the new database. And AWS has tooling to help with this. There's something called the database migration service that we used as a building block. And it can do schema conversion and copy. It can migrate data. It can even validate the data. And then in theory, all you have to do is point the application. However, when it comes to the real world, things start to get a bit more tricky. So in our case, we had over 100 applications of different data sizes. And each application, at least from the database perspective, is very different. The data shape is not always is very different. The data access patterns are different. And if you do this naively, you can run into different issues per database. And you don't want to do that. You want to catch issues early as much as you can. And these applications are written in different languages. We can't just build something for Java and ignore all the other use cases out there. You have to make sure you build something, at least for us, for all the languages that'll work in all languages. And you don't want to build something individually in each language. You want to find a way to support all these use cases together. Additionally, these different applications have different downtime requirements. Some are OK with being down for 4 hours in a weekend. They're cool with that. Others are like, oh, we can't support more than 2 minutes of downtime or 30 seconds of downtime, so it gets kind of tricky. And these applications also don't exist in a vacuum. For every application database, there's often streaming connectors, there's analytics connectors. And again, if you did this naively, we'd migrate the database and then say, hey, app team, you're on your own to migrate your Iceberg exports or Flink jobs and things. And we have a lot of this at Netflix. So you have a whole data platform of all these pieces that you can just plug into your database. And so that's where it gets kind of tricky. And so now we've talked enough, I think, about what we try to solve and why. Let's talk about how we solved it. And we're going to go over this in sort of 3 sections. First, we'll talk about what we did before even involving app teams, what sorts of pre-work we can do before talking to this team so we can minimize the back and forth. We'll talk about how we copy the schema and the data. And spoiler alert, we leaned heavily on DMS for this with some additional tooling on our end. And then we'll talk about how we validated the data as all there, and then did a live-ish cutover, live to the point where reads continue to work throughout the entire process. Writes is what we took down for a few minutes. So let's jump right into the pre-flight checks. So this is something we did before even involving app teams, and we did this across the entire fleet. Hundreds of databases. We did this upfront just so we can minimize the back and forth. We used AWS DMS tooling. They have this thing called the schema conversion tool that you can run across a database on a database and say, hey, generate a report. Like, will this work with this as the source and this as the target? So our target obviously is Aurora Postgres. AWS actually did not support the source that we use because it's a third-party piece of software. And so we worked with them to build in support so we run this migration. So this generated a report with, this index is not going to work in Aurora Postgres, or these hidden columns will become visible columns. And so we were able to take these and work with the app teams to make sure their schema would work on the source and target. And so that was pretty helpful. The second piece is, so now that you have the schema done, you have to worry about the data. So application teams, were executing SQL statements against all of their like third-party databases. We were able to take those, sample them, and without app team involvement, and run them against Postgres, basically, to sort of see would this actually work. And so this gave us some confidence that the schema will work and the sort of schema changes will work as well. We also did the work of looking at their source cluster up front and provisioning the target clusters based on the traffic patterns we saw. So we knew how to size this Postgres database instance on the target end. We copied over all the ownership metadata. We copied over all the authorization information that we needed to make sure their apps could talk to the database. And not only did we provision these final clusters, we provisioned a temporary cluster as well. And we took that temporary cluster, we copied over the schema and data, which we'll go over in a second, and validated it. And we handed those off to application teams because there's only so much you can do by looking at the schema and the data. You actually have to run your application to see how does the database perform? How does all the SQL actually work? And we found a whole bunch of issues with implicit casts working in the old database but not working in the new. And so those are sort of the three ways we tested this. And again, across the entire fleet before even talking to application teams. The next thing we have to do is the actual schema and data copy. And this is where, let's say schema copy, we built tooling around AWS DMS. The schema copy is any database object, so tables, views, sequences. And because we're switching database engines, some of these have to be converted. They're not, it's not always one-to-one. So this is an example of conversion that we didn't do ourselves. AWS DMS did it for us, and it just copied things over. We did, however, build in verification because, especially because they didn't technically support this. We found all these edge cases where things were, getting mangled during copying. So, for example, we had a varchar 3 that was converted to a varchar 1, which, what's the impact of that? These were country codes. You can't really have a country code that is just C. That's not going to work. And so we found these sorts of things by writing our own schema verification tooling to sort of double check the work that we were doing because we were on the hook for this with our app teams. The next thing to do is the actual data copy. And this is, again, where we built tooling around DMS. And DMS does a full load, which is a sort of point-in-time copy over of all the data and the source to the target. It also does CDC, which is change data capture, which is as the application is writing to the source database, it's being replicated over to the target. Keep in mind, this is a live migration, and so we're not shutting down the application and then copying the data. We're doing this live. So application is running, the database is running, the source database is running, and the target, and so we copy data and then start replicating it. We did, similar to earlier, we did build in some tooling on our end. So we built in specifically some monitoring tooling because we found that in some cases the task would fail partway through because of a transient issue, and we wouldn't realize until it's time to cut over and be like, oh no, database replication isn't happening, we need to abort. And so this helped us find issues earlier instead of doing during a cutover. Now, just because the data is all there doesn't mean you're done. You actually have to validate the data is all there. And remember, at this point, we have a source, we have a target, we have data being replicated from the source to the target. But effectively, we have two different databases with very similar data sets, maybe not exactly the same, but that's what we need to find out. And we kind of learned this the hard way. we found issues up front. So DMS does support validation, except one, it wasn't built for this third-party source database. And two, we wanted to do it without putting pressure on the source and target because these are live databases, at least the sources initially. And we also wanted to make sure this works well for both large and small data sets in a reasonable amount of time. And so what we did is we used a lot of existing infrastructure, and we took those source and target databases and attached them to a data feed. So think Kafka, for example. Actually, Kafka, not in this case. But so we connected them to a data feed so that we sort of dump the data and then also do CDC from there. And we sent that to our data warehouse. Now it's in a data warehouse. We don't have to worry about putting pressure on the source database because we can write a giant distributed SQL join across two tables to say, hey, for these two tables, what data is different? Like, we need to make sure that everything matches. But again, since this data is changing over time, we sort of cut off, let's say 5 minutes in the past and say if any records have come in within 5 minutes, ignore them. Everything else, let's validate the entire data set. And so we can do this faster, and we can do this sort of out of band as well because we're taking a cutoff at a certain point anyway. But obviously, that's only part of the problem. The second part is how do we validate that data that's still coming through and also the most recent data is still correct. And so this is where live validation comes in. So we take those same two data streams, which again are processing data coming in to the source from the user and to the target from the source through replication. And we pipe them into a validator. Under the hood, this is a Flink job, but a validator that is taking the two streams, source and target, and comparing them. So for each record we see in one stream, let's make sure we see the equivalent record on the other stream. And this is a lot faster than doing the entire data set in one fell swoop. And so this lets us, you'll see later on, do the cutover much faster because we can be confident that the data before is valid and the data that is going through is valid. Now, once we've, the last detail is this is the full picture of our validation. We have the data streams going and both the batch validation and online validation happening at the same time. OK, we have validated our data. Let's talk a bit about the cutover. And the way we realized we can do this is zero downtime for reads and minimal downtime for writes. But to do this, there's sort of two pieces of this. One is we need to take the application out of the loop as much as possible. We don't really want to be sitting on a call with the app team and coordinating things back and forth. And it's just a mess because they have to shut off the app. So we realized if we can move them out of the loop faster, we can do a lot more things on our end. And then the second part is just automate. It's one thing to do one migration. It's another by hand. It's another thing to do like 100+ migrations. And so let's go over both of these. So for the cutover process, before I get into it, one thing we tend to do at Netflix is we run proxies in front of data stores. And we do this in a lot of cases just to do auth-in, auth-z, so authentication, authorization. But depending on the data store, it might have some other functionality as well. So we realized that in order to get the application out of the loop, if we handle things at the proxy layer, that lets us take the connection from the proxy to Postgres and repoint it to Aurora without the application being involved. To do that, you have to make sure that the application will work with both the source and the target. And so at this point, we have to make sure that the previous schema checks and SQL checks are passing. Everything there is good. They've done all their testing with a temp cluster. And then we make sure that they're talking to the proxy. And this makes it so that, so if they're talking to the proxy, we control the proxy. We can control the cutover time and shut off writes and do all that fun stuff without the application team being involved. And we also have to make sure that using the correct credentials all work on the source and target. So this lets us do cutover without the application being involved. Now let's go over the actual cutover process. And this is a lot of steps. So again, I'm going to blaze through it. But let's see how far we can get. So remember, at this point, we have source and target, replications happening from the source to the target. The first step is, hey, how long is that replication delay? We don't want to attempt to cut over if the replication delay is like an hour, because then you're sitting and waiting for an hour for replication to catch up. And so what we do is we write a record into the source and wait for it to show up in the target. It's that simple. And we're using an internal metadata table that we create so that we don't mess with the user's data. And we set an arbitrary-ish cutoff as a minute, but in reality, we saw in most cases it was 15, 16 seconds of replication delay. And this is, we measure this so we know it's accurate. Once we know that the replication is happening, we have to run our validation. And I talked about this earlier. We have batch and online validation. At this point, remember, the application is still running. Everything is up. Nothing is down. And so we just run our batch validation, make sure that the data we copied over is accurate. Assuming it's accurate, we have to make sure that the user is still actually talking to the proxy. And this is us trying to remove all the foot guns from the user, because we found cases where users were not talking to the proxy, or they had some app that was running on a batch schedule. And we ran some checks to make sure no one is talking directly, but we also removed direct access and made it so they had to talk to the proxy. And this made it more difficult for users to mess things up later on by sort of a split brain scenario, talking to the wrong cluster. And then the last step is I talked about how databases they don't exist by themselves. And so we take all that streaming and batch infrastructure and copy it over from the source to the target. Because at this point, we know that the data is all there. It's correct. Replication's happening. So it's safe to do that. All you're doing is introducing another few seconds. If the replication delay is 15 seconds, you're adding 15 seconds of delay to their downstream pipelines. That's fine. No one's going to care. No one's going to notice. This gets us to the critical section. At this point, we shut off writes. And we just sort of did this by modifying permissions for the user on the source database. And so reads is still working, so the application is still up, but it's slightly degraded because writes aren't working anymore. And we did coordinate with app teams on a downtime window for this, but applications again up and writes are blocked. And then I talked about sequences briefly earlier. Sequences are basically stateful counters in the database, and they don't get copied over by replication. So you have to take the sequences from the source, then make sure the ones in the target, the values match up to what they're supposed to be. Sort of a small detail. And then I mentioned earlier we measured replication delay. We now have to wait for replication to catch up. And it's the same process as before. We push a record into the source, wait for it to show up at the target. At this point, we've blocked writes, so we know that the record we pushed in is the last record. So when it comes through, we know we're done with replication. And then we look at our validation, but this time we look at only online validation, because we previously verified batch validation and also online at the time. At this point, we're just saying, hey, is the data still correct? Is it still not mangled? Do we have confidence that we can cut over safely? Assuming that's true, we're essentially done. We take the proxy, we update it to point to the target, which is, in this case, Aurora Postgres. And we also terminate connections on the source database just to make sure there are no lingering connections, because a lot of our stuff is done at connection time. And so we kill all connections, and now the application is talking to the target. We never turned off writes to the target, and so it just magically starts working. And that was a cutover process. That was a lot. And so I'll leave you with how far we are, because we're not done, and learnings we have from this adventure that we've been on. This has been, we started writing the automation, I think, December last year, so almost a full year, but we ran our first migration in April. It was kind of janky, some manual code running on my laptop, some running on Jupyter notebooks, but we made it work. And then we built pieces as we went. But at this point, we're over 90% complete. There's a handful of cases that require some special handling, large data sets that we'll be finishing off in the next few weeks. But I'm pretty impressed with this progress on our team. We did not think we'd be this far right now. Additionally, we've seen this in some cases, not all. We saw in some cases, latencies drop. And this is partly because this is no longer a distributed store. We're not doing Raft consensus for reads and writes, and Aurora Postgres, you're generally reading from memory. So there are reasons for that, but this is sort of a side benefit is latencies are generally lower in a lot of cases. And you can kind of see it's pretty obvious from this graph when the cutover happened. There's a very clear demarcation. And this is critical for us as the data platform team. Is we found a number of data corruption bugs, and we fixed them all as far as we can tell. I mentioned earlier that we ran our temp cluster creation across the entire fleet. That included validation, and that found 10-ish data corruption bugs. Some were with null handling of columns, some were encoding getting mangled, some were generated columns not being copied over correctly, some were data truncation, columns just being dropped. And we found all these up front. Well, almost all. There were a couple we found later on. There's one weird one with statements in a transaction being ordered differently depending on when they came in through replication that we found when we were doing test cutovers, because that's CDC related. Our initial process was less CDC and more just full load. And so I'm pretty happy with this because we found all these bugs early on without going back and forth with the app teams. We worked with the DMS folks because sometimes it was edge cases on their end. Sometimes it was engine differences that we had to work around. But we got all these sorted and validation passed. And after all that, no rollbacks, which is I'm pretty proud of. We had a couple of fixed forward use cases. It wasn't all sunshine and rainbows. Some of them were just underscale clusters. Some of them were metadata didn't get copied over correctly. We fixed all of those, but everything happened and no one had to roll back. And so the last thing I'll leave you with is that initial fleet-wide dry run we did was amazing because it saved months of time. I'm not even exaggerating. By doing this all up front across the fleet, working with the DMS folks, building resiliency into our tooling, and that all worked really well. We built on top of a lot of existing tooling, DMS, some of our own tooling as well. But we got a lot of value out of building verification and making sure things actually worked correctly. And the last piece is I mentioned earlier, we focused on the lowest common denominator of sorts and built things that would work across applications, across technologies. But we did spend some cycles building specific tooling for like Java Flyway because it turned out a lot of folks at Netflix use that. And so we built some specific tooling just for that, even though it's not really applicable to all use cases. But yeah, that's all I have. Thank you.
Thank you very much.